Welcome to CyberExplain channel. Today we are going to discuss OAuth2 and OpenID Connect, securely delegate access. You know how frustrating it is when you want to use a cool new app, and it asks for your username and password for another service? Like a photo editor needing access to your cloud storage, or a fitness tracker connecting to your social media. Giving away your primary credentials everywhere is a huge security risk. If one of those apps gets compromised, suddenly your main account is exposed. That's where protocols like OAuth2 come in. They're designed to solve this exact problem by allowing you to grant specific permissions without sharing your actual password. It's like giving a valet a special key that only opens the car door and starts the engine, but doesn't unlock the trunk or the glove compartment. So, what exactly is OAuth2? Think of it as a framework that lets a user authorize a third-party application to access their data or perform actions on their behalf, without actually giving that third-party app their username and password. It's all about delegation. The user, the resource owner, is still in control. They decide what the third-party application, the client, can do. The service providing the data or functionality, the resource server, issues special tokens to the client, which act as temporary passes. This keeps your primary credentials safe and sound, stored only with the resource owner and the identity provider. To really get OAuth2, we need to meet the key players involved in this dance. First, there's the resource owner, that's you, the user who owns the data. Then, we have the client, this is the third-party application or service that wants to access your data, like that mobile banking app we'll talk about. Next up is the authorization server, which is the gatekeeper. It's responsible for authenticating the resource owner and issuing access tokens. Finally, we have the resource server, this is where your actual data lives, like your bank's transaction API. The authorization server and resource server are often the same entity, especially within a single organization's infrastructure. Now, how does the client actually get that precious access token? OAuth2 defines several grant types, which are basically different flows or methods for obtaining tokens, each suited for different scenarios. Ever wondered why some apps use pop-ups, while others redirect you? It's all about the grant type. We've got the authorization code grant, which is super common for web and mobile apps where the user is directly involved. Then there's the client credentials grant, perfect for machine-to-machine communication where there's no human user directly interacting. We'll break these down, but remember, the goal is always to securely get that token without exposing sensitive credentials. Let's dive into the authorization code grant type, because it's the workhorse for most user-facing applications, especially web and mobile apps. When you click Login with Google or grant access to a new service, you are likely using this. The flow starts with the client redirecting you to the authorization server. You log in, and then the authorization server asks if you are okay with the client accessing your data. This is consent. If you agree, the authorization server sends back a one-time use authorization code to the client. The client then exchanges this code, along with its own credentials, with the authorization server for an access token and sometimes a refresh token. This is a two-step process for better security, preventing the code from being exposed directly to the user's browser or device. Now, for when your application needs to talk to another service without a human being in the loop, think of microservices communicating or a scheduled task needing to pull data. That's where the client credentials grant type shines. Here, the client application authenticates itself directly with the authorization server using its client ID and client secret. If successful, the authorization server issues an access token directly to the client. No user consent, no redirection, just a secure exchange between two machines. This is vital for backend processes, API integrations, and scenarios where the client is acting on its own behalf, not a user's. While authorization code and client credentials are the most common, it's good to know about a couple of others. The resource owner password credentials grant type is a bit of a no-no in most modern architectures. It's where the client asks for your username and password directly, then sends them to the authorization server. This essentially defeats the purpose of OAuth2 by having the client handle your credentials. Use this only in very specific, trusted scenarios, usually for legacy apps. The implicit grant type, historically used for JavaScript apps in browsers, is also largely deprecated due to security concerns. It's less secure because the access token is returned directly to the client in the redirect URI, making it more susceptible to interception. Stick to authorization code whenever possible. One of the most critical components of OAuth2, especially in user-facing flows, is consent. This is that moment where the authorization server says, "Hey, this app wants to access X, Y, and Z. Do you approve?" It's your explicit permission. Think about it, would you want an app to just start pulling your bank transaction history without you even knowing? Probably not. Consent ensures you are aware of what data is being accessed and by whom. It puts you, the resource owner, in the driver's seat. Good OAuth2 implementations make this consent screen clear, showing exactly what permissions the client is requesting, so you can make an informed decision. Consent is about if you approve. Scopes, on the other hand, define what the client is actually allowed to do. Imagine your bank app. It might have scopes like read_transactions, transfer_ funds, or view_ balances. When the client requests authorization, it specifies the scopes it needs. If you grant consent, the issued access token will be restricted to only those scopes. This is the principle of least privilege in action. Even if a client could do more, it's only granted the specific permissions, scopes, it requested and was approved for. This fine-grained control is key to secure delegated authorization. So, we've gone through the flow, and the client has an access token. What is it? It's a credential that the client presents to the resource server to gain access to protected resources. Think of it as a temporary VIP pass. These tokens have a limited lifespan, they expire. This is a crucial security feature. If a token is intercepted or leaked, it's only useful for a limited time. Access tokens are typically strings of characters, and while they can be opaque, just random strings, or structured, like JWTs, their primary job is to be presented to the resource server for authentication and authorization. The resource server then validates the token, often by checking its issuer, expiry, and the scopes it grants. Access tokens expire, right? So, what happens when a user has an app they use frequently, like their banking app? Do they want to re-authenticate and reconsent every single time? That would be a terrible user experience. That's where refresh tokens come in. A refresh token is a longer-lived credential that the client can use to obtain a new access token once the current one expires. The client securely stores the refresh token. When the access token is no longer valid, the client sends the refresh token to the authorization server, which, if valid, issues a fresh access token. This allows for continuous access without requiring constant re-interaction from the user, while still maintaining security by having a short-lived access token in active use. Access tokens can come in two main flavors, opaque and JSO web tokens, JWTs. An opaque token is just a random string. The resource server receives it, and if it needs to know details about the token, like scopes or expiry, it has to make a separate call back to the authorization server. This is simpler for the client and authorization server but adds latency for the resource server. A JWT, on the other hand, is a structured token that contains claims, pieces of information about the user, the client, scopes, expiry, etc., all signed by the authorization server. The resource server can often validate the JWT's signature and parse the claims directly without calling back to the authorization server. This makes token validation faster but requires the resource server to trust the JWT issuer and be able to validate its signature. Okay, so OAuth2 is fantastic for *delegated authorization *, letting one app access another's resources on your behalf. But what if you want to know who the user actually is? What if you need to verify their identity? That's where OpenID Connect, OIDC, comes in. OIDC is an identity layer built on top of the OAuth2 framework. It uses OAuth2's flows but adds an extra piece of information, an ID token. This ID token is a JWT that contains verifiable claims about the authenticated user, like their name, email, and a unique identifier. So, while OAuth2 grants access, OIDC verifies identity. This is a crucial distinction. An access token, issued via OAuth2, is primarily for *authorization*. It tells the resource server what the client can do*. An ID token, introduced by OIDC, is for *authentication*. It tells the relying party, usually the client application, who the user is. The ID token is a JWT signed by the authorization server, and it contains claims about the user's identity. The client application receives both. It uses the access token to call the resource server, and it uses the ID token to verify the user's identity and potentially personalize the user experience within the client app itself. They serve different, albeit complementary, purposes. While the ID token gives you essential identity claims, sometimes you need more detailed information about the user. OIDC defines a standard endpoint called the UserInfo endpoint. After the client has obtained an ID token and an access token, using an OIDC-compatible OAuth2 flow, it can use the access token to make a request to the UserInfo endpoint on the authorization server. This endpoint returns a JSON object containing a set of claims about the authenticated user. This is useful for richer profile information that might not fit or isn't appropriate to include directly in the ID token, keeping the ID token lean and focused on essential identity verification. Let's bring this all together with our mobile banking app example. Imagine you've downloaded Secure Bank app and want to view your transaction history. Instead of asking for your bank username and password directly, which would be a huge red flag, Secure Bank app uses OAuth2 and OIDC. When you initiate login, the app redirects you to the real Secure Bank's authentication portal. You log in there with your actual bank credentials. The bank's authorization server then shows you a screen. Secure Bank app wants to view your transaction history. Allow. You tap Allow. The bank's server issues an authorization code to Secure Bank app. Secure Bank app exchanges that code for an access token to read transactions and an ID token to know it's you logged in. Now, Secure Bank app can use the access token to fetch your transactions from the bank's API, all without ever seeing or storing your bank password. Continuing our banking app scenario, after you approve the request, the bank's authorization server sends an authorization code back to Secure Bank app. This is like a temporary ticket. Secure Bank app then takes this code and sends it, along with its own client credentials, its secret identity to the bank's system, to the bank's token endpoint. The bank's token endpoint verifies the code and the client's credentials. If everything checks out, it issues two tokens, an access token, specifically for reading transaction history, with a limited scope, and an ID token, containing your basic user identity information. Secure Bank app securely stores these tokens. It then uses the access token in subsequent API calls to the bank's transaction history endpoint. This is super important, folks. How the client application handles these tokens is critical. For native mobile apps, storing tokens securely is a big challenge. You can't just put them in plain text. On iOS, you'd use something like the keychain. On Android, the Android Key Store system. For web applications, if using the authorization code grant with a backend, The tokens are typically exchanged on the server side, and the user gets a session cookie. If it's a single-page application, SPA, using authorization code with PKCE, tokens might be stored in memory or within secure browser storage mechanisms, being careful to avoid common pitfalls like local storage for sensitive tokens. Refresh tokens, being long-lived, need even more stringent protection. You might have heard about PKCE, Proof Key for Code Exchange. This is a vital extension to the authorization code flow, especially for public clients like mobile apps and single-page web apps that can't securely store a client secret. How does it work? Before starting the flow, the client generates a code_verifier and a code_challenge, a hashed version of the verifier. It sends the challenge to the authorization server during the initial redirect. When it exchanges the authorization code for tokens, it also sends the original code_verifier. The authorization server hashes the verifier and compares it to the stored challenge. If they match, it proves that the client exchanging the code is the same one that initiated the flow, preventing authorization code interception attacks. Let's talk about how attackers try to break these flows. A classic attack on the authorization code grant, especially without PKCE, is authorization code interception. Imagine a malicious app on your phone, or a compromised browser extension, that can intercept the redirect URI after you approve access. If it snags that authorization code before your legitimate app does, it can then use that code to get an access token for itself. This is why PKCE is so crucial for public clients. It ensures that only the original client can successfully exchange the code, even if an attacker intercepts it. Another related attack is Open Redirect, where the attacker tricks you into authorizing access to a malicious site by manipulating the redirect URI. Once a token is issued, it's a valuable secret. Token leakage happens when an access or refresh token falls into the wrong hands. This could be through insecure storage on the client, logging errors, or an attacker gaining access to the client's system. If an attacker has a valid token, they can impersonate the user or client until the token expires. Then there's token replay. While access tokens are short-lived, a malicious actor might try to reuse a stolen token if the resource server doesn't properly validate its expiry. Refresh tokens are even more dangerous if leaked, as they can be used repeatedly to generate new access tokens, effectively giving the attacker long-term access. What if the authorization server itself is compromised? This is a catastrophic scenario. If an attacker gains control of the authorization server, they could potentially issue fraudulent tokens to themselves or any client, allowing them to access resources they shouldn't. They could also tamper with consent mechanisms or steal all refresh tokens. This underscores why the authorization server is the most critical component in the entire OAuth2 OIDC ecosystem and needs the highest level of security. Imagine the main bank vault being compromised. That's the scale of impact here. How do we even know if something's going wrong? Detection is key. We need to monitor the issuance of tokens. Are there an unusually high number of new access tokens being generated? Are refresh tokens being used excessively to mint new access tokens? We also need to monitor token usage patterns. If an access token granted for read_transactions is suddenly being used to try and initiate transfers, that's a massive red flag. Logging at the authorization server is paramount. Record every token issuance, every refresh request, and every access token validation failure. These logs can then be fed into CM systems for anomaly detection and alerting. Another detection vector involves looking at consent. Are users suddenly revoking consent for a large number of applications? Or conversely, are there unusual patterns of consent being granted to applications that have never been used before, or to applications known for malicious activity? Monitoring these consent patterns, especially in aggregated logs, can help identify compromised accounts or malicious clients attempting to gain unauthorized access. If a user typically only consents to a few trusted apps, but suddenly starts granting access to dozens, something is likely amiss. Let's consider what happens when things go wrong with tokens. The most straightforward failure mode is an expired access token. The client tries to use it, the resource server says nope, you are too late, and rejects the request. A more active failure mode is token revocation. If a token is compromised, or a user decides they no longer want an app to have access, the authorization server can revoke that specific token, or even all tokens for that client user. When the resource server receives a revoked token, it's treated the same as an expired one. Access is denied. Implementing robust token revocation mechanisms is critical for incident response. It's not just about attacks. Sometimes, things break because the client application itself is misconfigured. Maybe the redirect URI registered with the authorization server doesn't exactly match the one the client is using. This will cause the authorization code exchange to fail. Or perhaps the client is sending an incorrect client_secret, or the scope requested is invalid or not permitted. These aren't malicious attacks, but they can certainly lead to a complete breakdown of the authorization flow, leaving users unable to use the app they expected to work. Proper validation at the authorization server is key to catching these misconfigurations early. The absolute cornerstone of any OAuth2 OIDC deployment is the security of the authorization server. It needs the strongest possible authentication mechanisms. Think multi-factor authentication, MFA, for any administrator accessing the authorization server's management console. For the API endpoints that issue tokens, robust client authentication is a must, using client secrets for confidential clients and mutual TLS or PKCE for public clients. It's not just about preventing attackers from getting tokens, it's about preventing them from even accessing the systems that issue them. We've hammered this home, but it's worth repeating. For any public client, that means mobile apps, SPAs, or any client that can't securely store a secret, always use PKCE. It's not optional anymore. The authorization code interception attack is too prevalent and too damaging to ignore. Make sure your authorization server supports PKCE and that all your client applications that are public clients are configured to use it correctly. It's a relatively small implementation effort for a massive security gain. Don't just throw broad scopes like all_data at your clients. Define your scopes as granularly as possible. If an app only needs to read transaction history, give it read_transactions. If it needs to transfer funds, grant transfer_funds. This is the principle of least privilege applied to API access. Regularly review the scopes your clients are requesting and the ones they've been granted. Are they still necessary? Are they too broad? This helps limit the blast radius if a client is compromised. Access tokens should have a short lifespan. We are talking minutes to hours, not days or weeks. This minimizes the window of opportunity for an attacker if a token is leaked. Crucially, implement your refresh token strategy carefully. Refresh tokens are powerful. They should be stored securely and ideally only used once. Upon successful use, the authorization server should issue both a new access token and a new refresh token. This is called token rotation. This invalidates the old refresh token, meaning if it was compromised, it can't be used again after it's been used once. If a refresh token is used that has already been redeemed, it's a strong indicator of compromise. As we touched on in detection, robust logging is non-negotiable. Log every token issuance, every token validation, success and failure, every consent grant and revocation, and every client registration. These logs should be centralized, immutable if possible, and regularly reviewed or fed into an alerting system. Look for anomalies, unusual token issuance rates, unexpected client IDs requesting tokens, frequent validation failures for specific tokens or clients, and sudden changes in consent patterns. Think of these logs as the forensic gold mine for any IAM-related incident. When you are working with cloud providers like Microsoft Entra ID, formerly Azure AD, AWS IAM, or Google Cloud IAM, they often provide managed OAuth2 OIDC services. The key is to leverage their built-in capabilities. Configure your applications to use Entra ID's app registrations for OAuth2 OIDC flows, AWS Cognito for user pools and identity federation, or Google's identity platform. These services handle the complex token issuance, validation, and management for you. Ensure you are configuring scopes, redirect URIs, and client secrets correctly within their respective consoles. You are essentially using a robust, battle-tested authorization server provided by the cloud vendor, which is a massive advantage. Ever notice that long, random string in the URL when you are logging in via Auth2? That's the state parameter. It's a vital security measure to prevent cross-site request forgery (CSRF) attacks. When the client initiates the authorization request, it generates a unique, unguessable state value and sends it along. The authorization server includes this state value in its redirect back to the client. The client then checks if the state it received matches the one it initially sent. If they don't match, it means the request might have been tampered with or hijacked, and the client should reject the process. It's like a secret handshake to ensure the user who started the process is the one completing it. So, in our mobile banking app scenario, what's the split? The initial login and consent flow, where the app asks the bank for permission to access your transaction data, that's primarily an OAuth2 flow. The bank's authorization server is issuing tokens that grant specific permissions, scopes, to the secure bank app. However, when that same flow also provides the secure bank app with an ID token confirming who you are, your name, user ID, etc., that's when OpenID Connect comes into play, building on top of the OAuth2 foundation. The app uses the OAuth2 access token to get your transactions, and the OIDC ID token to know who the logged-in user is within the secure bank app itself. Not every user interaction goes smoothly. What happens if, during the consent step, the user clicks deny? The authorization server will redirect back to the client application, but it will include specific error parameters in the redirect URI. Typically, this will involve an error parameter, often set to access_denied and potentially an error_description to give more context. The client application must be designed to gracefully handle these error responses. It should inform the user why access was denied and perhaps suggest alternative actions or retry options. It's crucial that the client doesn't try to force the user or enter a broken state. When a token, especially a JWT ID token or access token, is issued, it often includes an odd audience claim. This claim specifies who the token is intended for. For example, an ID token issued for the Secure Bank app would have an odd claim that identifies Secure Bank app as the intended recipient. When the token is presented to a resource server or the client application, they must validate this odd claim. If the odd claim doesn't match the entity receiving the token, it's a security violation. That token is not meant for them. This is a fundamental check to prevent tokens from being used by unauthorized clients. We mentioned the implicit grant type earlier, but it's worth re-emphasizing its deprecation. Historically, it was used by browser-based JavaScript applications because they couldn't securely store a client secret. The flow worked by redirecting the user, and the authorization server would append the access token directly to the redirect URI in the browser's address bar. The JavaScript in the page would then parse this token. The problem? The token was exposed in the browser history, accessible to malicious JavaScript on the same origin, or even through other vectors. For modern sparse, the authorization code grant with PKCE is the secure, recommended alternative. It keeps the sensitive code exchange on the client-server boundary, or within the browser's secure context, not directly in the URL. Similar to the OD claim, the issuer claim in an ID token or access token is critical for security. It identifies the entity that issued the token, in our case, the bank's authorization server. When a client application or resource server receives a token, it must verify that the claim matches the expected issuer. This prevents a scenario where an attacker might try to trick your client into accepting tokens from a fraudulent authorization server. By checking the claim against a pre-configured, trusted list of issuers, you ensure the token is legitimate and originated from a trusted source. We've talked about clients needing to authenticate themselves to the authorization server. How do they do it? For confidential clients, like backend web servers that can securely store secrets, the common method is using a client_ID and client_secret. For public clients, mobile apps, SPAs, that cannot securely store secrets, PKCE is used to secure the authorization code grant flow. Increasingly, mutual TLS, MTLS, is also being used, where both the client and server present certificates to authenticate each other. This is a very strong form of client authentication, often seen in machine-to-machine scenarios or very security-sensitive environments. Security is an ever-evolving field, and so are these protocols. OAuth 2.1 is the next iteration, aiming to simplify and harden OAuth 2. Key changes include deprecating the implicit and resource owner password credentials grant types entirely, making PKCE mandatory for authorization code grants, and requiring the audience OD parameter in token requests. It also aims to clarify security requirements and improve interoperability. While 2.0 is still widely used, understanding the direction of 2.1 is important for future-proofing your IAM strategies. It's all about tightening security and removing ambiguities. So, to wrap it all up, OAuth 2 provides the framework for secure delegated authorization, allowing applications to act on your behalf without holding your primary credentials. It's all about grant types, consent, scopes, and carefully managed tokens. OpenID Connect then layers on top of this to provide verifiable user identity through ID tokens, making sure you know who is accessing what. Together, they form the backbone of modern secure authentication and authorization for web, mobile, and API interactions. By understanding these protocols, their flows, and their security implications, you are well on your way to building more secure and robust applications. Thanks for watching. Subscribe to the CyberExplain channel. See you on the next video.